Hello and welcome to lecture 6. This is of Ramanujan Explained. This is about Ramanujan's one psi one sum. So this is what the sum looks like. And let me begin immediately. Last time we were considering infinite products. So the last time we had we were considering the theory of infinite products when they converge, etc. So here are we begin with some classic infinite products. So this is the first one is due to Wallace, and all this is somewhat relevant to what we are going to do today. This is in 1656, and Wallace had this product for sine phi z is equal to 1 minus c square over n square, and going from 1 to infinity. Why does it converge? So it converges because summation c square over n square is converges for all values of c. So it converges, absolute convergence is guaranteed by this theorem, which we did. And you notice that the zeros of sine phi z and this product are when z is 0, plus minus 1, plus minus 2, and so on. The second classical product, which we have not done yet, but we will do at some point, is Weierstrass's product for 1 over gamma z. And this is z e raised per small gamma z. So this is Euler's Euler-Mascheroni constant product as n goes from 1 to infinity, 1 plus v over n e raised per minus c over n. So again, by one of our theorems, this converges. So we consider log of this product. So we can ignore these terms maybe. And we take log, and this is log of. So this is z by n minus c square by n square plus c cubed by n cubed, and so on. And minus z by n. And whatever we get, we can show. So the first term cancels, and the rest we can show converges. So we will give more details later, but notice that the zeros here are at z equal to 0, minus 1, minus 2, minus 3. So half of these zeros are the zeros of gamma 1 over gamma z. The third product is the theta product. So the theta product is theta of cq, which is zq infinity and q over zq infinity. This product is 1 minus c q to the k minus 1, 1 minus q to the k over c, k going from 1 to infinity. And the zeros are at z equal to 0, q raised per plus minus 1, q raised per plus minus 2, and so on. And again, converges. We showed this converges because the summation q raised per k converges. So both these products independently converge for z not equal to 0 and q less than 1. And notice that how is this related? I mean, it's very natural from what we've been doing. So the previous guys have got, they have zeros at arithmetic progression, and here we have zeros at a at a geometric progression. So, again, these are absolutely convergent by what we did. So here's an exercise. Show that these are all the zeros. So I will outline a proof due to Rosengren in his tutorial, which shows this, but it's not obvious. It could have more zeros in general. So this may be a interesting thing. So we note that theta of CQ is a meromorphic function. So at z equal to 0, it's not defined. And so has a, but otherwise is analytic. So has a Laurent series expansion of this family. So summation an g raised per n going from minus infinity to infinity for z not equal to 0. And in fact, I'll just write it here. Make it very quicker. So in fact, theta of CQ is, so this is Q over Z Q infinity. This is the Laurent series expansion is given by this identity minus 1 raised per n, q raised per n minus 1 over 2, z raised per n. So this is called Jacobi's triple product identity, and the sum here, if you notice, this sum is called a bilateral sum. So it goes from minus infinity to plus infinity, and this is Jacobi's triple product. And the identity that we are going to discuss by Ramanujan is a more general version of this. So more general. So first of all, let's try to understand what are bilateral sums. So so far we have seen series of the form summation k going from 0 to infinity, something on the top, then we have QQN at the bottom, something else, and maybe z raised per n. And so these series are infinite in one direction, but recall that if you have q raised per minus n qk in the summand, then q raised per minus n qk is equal to 1 minus q raised per minus n, 1 minus q raised per minus n plus 1, and so on. 1 minus q raised per minus n plus k minus 1. It's 0 if k is bigger than n. So if this term is there, the RPS series with q raised per minus n as a numerator parameter terminates naturally. From above. So the sum goes from 0 to n if it has something like this, and we'll claim this chap 1 over QQK makes the series terminate naturally from below. What that means is that when n is negative, when k is negative, then this should be 0. So why is that? So for that, we need to extend the definition of the Q rising factorials for any complex numbers, and this is how they are defined. A q to the z infinity. This is for absolute value of q less than 1. So these are infinite products which are defined and we can define AQZ now. And notice that when Z is equal to N, then this reduces to the previous case, right? So AQN. So now, so 1 over QQK would be QQ infinity, and on top you will get Q raised per K plus 1 Q infinity, and this will be 0 if K is -1, -2, -3, and so on. So, right, so we so this makes sure that the sum terminates. So for example, we had this sum K going from 0 to infinity, the binomial theorem, AQK over QQK, 0 is for K, and this was equal to AZQ infinity over ZQ infinity. So for absolute value of Z less than 1. So remember this is the binomial theorem. And this 1 over QQK actually normally it terminates. So so it's natural. So the sum being considered now, the sum we consider now is you choose AQK, and then in the bottom you just have an arbitrary parameter K, Z raised per K, and K going from minus infinity to infinity. So this is a bilateral sum. So this one is, of course, so this is bilateral, and it generalizes the simplest of the sums, the binomial Q binomial sum. So it's sort of natural to consider this. All right. So when does it converge? First. Okay. So so note that. First of all, for K negative, suppose well, say K is positive, but we consider AQ of minus K. So what does this mean? By definition, it is this. This is AQ to the minus K, Q infinity, and this is AQ infinity. So you have 1 minus AQ to the minus K, 1 minus AQ to the minus K plus 1, and so on. And 1 minus AQ to the minus 1, and the next one will be the same as AQ infinity, the rest of them. So this cancels. So this is 1 over AQ to the minus KQK. And by reversing the sums, we can also write it as -1 to the K. So all the minus A to the K, Q raised by minus K plus minus K plus 1, so on up till -1. And then reversing the things, we get Q over A, QK. So this is equal to -1 to the K, A raised by K, putting this on the top, so it's 1 plus 2 plus so on, so it's K into K plus 1 over 2. And then in the denominator, you have Q over A, QK. So this is an important identity which we use to play around with this. So this identity. Now using this, we get the sum which we started with, AQK over PQK, Z raised per K, and we write it as K going from 0 to infinity, AQK over PQK, Z raised per K, and then the negative terms, K going from 1 to K, AQ minus K, EQ minus K Z to the minus K, and just write it here. This is equal to K going from 0 to infinity, AQK over PQK. And then using the simplification that we did, it's Q over PQK, Q over AQK, and A over B over AZ raised by K. So this guy over here, this chap, this we did by the ratio test, it converges. So it converges for absolute value of Z less than 1, and this chap converges when absolute value of B over AZ is less than 1. So the convergence conditions are B over B is less than AZ and Z is less than 1, or we can say 0 B over A is less than Z less than 1. It converges. So here's a exercise. We define, instead of RPR, let's define RCR with R numerator parameters and R denominator parameters as this bilateral sum A1 to AR are the numerator parameters. So numerator, you have this. So there's no extra Q. And using the same idea, find the convergence conditions. The region of convergence. Okay, so very well. What we are going to do is we are going to prove a result for the 1 psi 1, which is due to Ramanujan, which we started with, and we will give a proof by Ismail. So Murad Ismail's proof is a very useful idea, and it was a discovery proof. So what is so let's discuss what is Ismail's idea. And it's very useful, so it's worth understanding. So we consider for n bigger than 0, this series, n going from minus infinity to infinity, AQK over Q raised per n QK, Z raised per K. So first of all, we notice that it is n going from, K going from minus n plus 1 to infinity, AQK over Q raised per n QK, Z raised per K. Why is that? Because if you consider Q raised per n QK, so again by the same approach, by its definition, what we did earlier, this is what the definition is, and this is 0 for K equal to minus n, minus 1, and so on. So the bottom terms drop out, and we get this. So this sum is equal to this, and then we can shift the sum. So the sum is K going from 0 to infinity. So we shift the sum. So it's K minus n plus 1 over Q raised per n Q, K minus n plus 1, and Z raised per K minus n plus 1. Very good. And now we split the term, so we use this AQ n plus or K plus m equal to AQK A q raised per k q m. So this is the elementary identity which works for, which we have done as an exercise before, it works for any integers. And we get the sum equals a q minus n plus 1, q raised per n q minus n plus 1, and the z raised per minus n plus 1. And then there is a sum k going from 0 to infinity, a q to the minus n plus 1 q k and q q k. So n minus n plus 1 will just give you q raised per 1 and z raised per k. And this is summable using the Q binomial theorem. So let me bring it here. This is equal to AQ minus n plus 1 over Q raised per n Q minus n plus 1, Z raised per minus n plus 1, AQ minus n plus 1, C Q infinity over Z Q infinity. So we've got an expression using Q binomial theorem, which we know. So we use the Q binomial theorem, which was entry, I think 2, entry 3.16.2 of Ramanujan. And then there is a series of small steps that you can take. And let me say this is an exercise. And you can write it as the following: AZ Q over AZ Q raised per n over A Q infinity, and the bottom you get G Q raised per n over AZ Q over A Q infinity. So let me call this double star. So we get this is equal to k going from minus infinity to infinity, a q k q raised per n q k z raised per k. Right. So so what is Ramanujan's theorem? This is k going from minus infinity to infinity, AQK over PQK z raised per k equal to, and what I'm doing here is I'm replacing q raised to the power n by p in this expression. Right, so if b is equal to q, you can see that it drops down to the binomial to the q binomial theorem. Let me call this equation 1, and this is valid for b less than az and z less than 1. Right, so this is Ramanujan's one psi one sum. Okay. And the proof is so Ismail's idea of the proof was exactly this, that he considered both sides as analytic functions of b rather than g. So the proof by Ismail is both sides of one are analytic for in B in uh, uh, in a disk near zero. So in an open set near zero, because B was less than AZ, provided this is happening. So for fixed A and Z suitably chosen. Right, and they agree on B equal to Q raised per N for N equal to 1, 2. This is the calculation which we did, so must be identical. So the proof is using this identity theorem, which I will write down just because it's so useful. So it's worth writing down. Let FZ and GZ be analytic. In a region, in a domain, omega, and suppose f of Zn is equal to G of Zn for a sequence Zn which converging to a point in the domain omega. Then f of Z is equal to G of Z for all Zn. So Murad Ismail has a tutorial called a brief introduction or review rather, brief review of Q series. It's a tutorial, and he explains how he uses this in many situations. So it's all right. So to summarize, the proof is simply you use the Q binomial theorem to prove a special case B equal to Q raised per N, and then by analytic continuation you get the desired result. So it's a discovery proof. What is very interesting is the discovery proof. What is also interesting is that Ramanujan, it's unlikely to be Ramanujan's proof. So Hardy said that Ramanujan did not have a knowledge of analytic functions until he came there. He came to England and he worked with Hardy. And then in the end, he said that he did gain a good knowledge of analytic function, what is known as analytic function theory, which is the complex analysis essentially. Okay, so how Ramanujan wrote this result. So this is theorem, and I'm repeating the theorem even though it's 16.17. So suppose PQ is less than Z is less than 1 over AQ, then one plus summation K going from 1 to infinity 1 over A Q square K. So very Ramanujan wrote it quite symmetrically. Minus AQ to the K Z raised per K plus summation K going from 1 to infinity 1 over B Q square K AQ square Q square K minus BQ to the K Z raised to minus K. This is equal to minus QZ minus Q over Z Q square APQ square Q square infinity minus AQZ minus PQ over Z AQ squared, PQ squared, Q squared infinity. So that's Ramanujan's one psi one. Now, a large part of Ramanujan's subsequent work, uses the following definition. So Ramanujan's theta function. Let A be an absolute value be less than 1. Then we define FAB as 1 plus k going from 1 to infinity, AB raised for k plus 1, k minus 1. K minus 1 over 2, A raised for k plus B raised for k, which could be written as a bilateral sum as follows. A raised for k plus 1 over 2, B raised for k minus 1 over 2. Okay, so we note that if you replace k by minus k, so minus k plus 1 becomes k minus 1. So write it here. Note that minus k plus 1 over 2 is k minus 1 over 2. So f of AB is equal to f of BA. So if we interchange A and B, if we just interchange A and B, it's the same thing as, just rewriting the sum from changing the order of the summation from k going from minus infinity to infinity, and replace k by minus k, we get the same thing. So it's the same, it's symmetric in A and B. And how Ramanujan wrote Jacobi's triple product identity. So that's his entry 1619 is FAB is equal to minus A minus B AB infinity. So proof you get from one psi one Ramanujan's form. So it's an exercise. I'll outline in the proof. So essentially, this entry 3, so 3 is volume 3, chapter 16.19 is Jacobi triple product identity. So which I think also I should write formally, Jacobi triple product. So let q less than 1 and c is not 0, then c q over z q infinity is equal to summation k going from minus infinity to infinity minus 1 raised for k, q raised for k minus 1 over 2, z raised for k. So so this proof I can indicate, take A going to minus z and B going to minus q over z. So AB is equal to q. If you do this in entry 3.16.19, you get this. And proof that converse that this is really Jacobi triple product entity. So Jacobi triple product implies this one is an exercise. Right. So so you show Ramanujan's identity from here. All right. So so we got where we started. Now So some definitions from entry 3.16 sorry, dot 22 1 to 4. So these entries are really he's talking about certain special cases. So these are definitions of what are called Ramanujan's theta products, theta functions. So he considered these special cases, and once I write them down, you will know exactly why. So phi of q is defined to be f q q, which can be written like this: q raised to power n squared, and going from 1 to infinity. So some squares, and using Jacobi triple product identity, you can show that this is the case. This is a result due to Gauss. Then another one of Ramanujan's theta functions is q cubed, which is k going from 0 to infinity, q raised to power k plus 1 over 2. And this again has a product formulation, q squared infinity, q squared infinity. So now again, these are the triangular numbers. And again, this is a result due to Gauss. Ramanujan considered that. Then the third one is equals f of minus q, this slightly contradictory notation, minus q square, which is k going from minus infinity to infinity, minus 1 raised per k, q raised per k into 3k minus 1 over 2. And this has a product form q infinity. So this is Euler's pentagonal number theorem. Pentagonal number theorem. So all these are proofs are in an exercise. They all follow from Jacobi's triple product identity, and they can be obtained from Ramanujan's form very easily. And in addition, he defined the fourth one, definition as again part of entry 3.16.22.4, fourth part. He defined this chi of q to be equal to minus q squared. So in the sequel, in the exercises, I will note down several things which you can get very easily over here using these functions, and that brings us to the end of this lecture. So to summarize, Ramanujan, this is Ramanujan's famous 1 psi 1 result, which is a result on bilateral series. And it's the first one non-trivial result which which was not a rediscovery of anything, and it contained Jacobi's triple product identity, which is very famous. It's also known to Gauss, as well as many of Gauss's original results on the squares and the triangular numbers, which are important in number theory. So if you take Gauss's function and raise it to the fourth power, for example, then you'll get a generating function of writing a number in the terms of as a sum of 4 squares. If you can show that every term is positive, then you know that using Lagrange's 4 square theorem. So such things were interesting to Ramanujan, and we will study them subsequently. All right. I can close this. Thank you very much.